Let me introduce our first presenter, Dr. Paul Doherty, who is a senior scientist at the Exploratorium. He's also a professor at San Francisco State University, and he's also the co-director of the Teacher Institute at the Exploratorium. In 2002, the National Association of Science Teachers in the United States presented Dr. Doherty with the Faraday Award for Excellence in Science Teaching. Dr. Doherty is an author and has published many books, including the Exploratorium Science Snack Book and the million-selling Exploro book. Dr. Doherty has also taught Tibetan monastics during the Sager Science Leadership Institute last May, and also returned again recently to teach the monastic graduates at the workshop that just preceded this conference. So please give a warm welcome to Dr. Paul Doherty.
Tasha Delay. I'd like to thank the monastic graduates, the Geshes, for being my students and teaching me for the last 2 weeks. Science has boundaries, and today I'm going to take you on a tour of a few of them. There are many boundaries to science, and it's important to realize that there are things beyond those boundaries. And the boundaries I'm talking about are the boundaries of physical science, physics science, and I'll introduce you to why they are the boundaries. And we're going to look, as I show in this slide, with our eyes, with telescopes, and with microscopes, to the big and to the small. This is a woodcut from 1888, and it shows the view of the universe from medieval times, that the stars were actually holes in an opaque black wall, and the holes let the light of heaven come through. But the scientist who actually made this woodcut is showing a pilgrim looking through the wall to find out what's on the other side. And that's what scientists are born to do, is to find the limits of science and look at what's on the other side. Science began in the late 1600s. The Royal Society got together. And there was lots of knowledge about the world before then. Some of it right, some of it's wrong. How do you find out the true from the false? So the Royal Society got together, and in their motto in Latin, it says, nullius in verba, don't take anyone's word for it, including mine. Do an experiment. That anytime you see a scientist and they say anything, you can always ask them, monastic graduates, what's the question? How do you know that? And the answer has to be a question. The answer to that question has to be an experiment. Now, to do an experiment, you must get the results. And out there in the universe, there are barriers to information flow. Information, we don't see it flowing across the edge of the universe. We don't see information flowing out of black holes. And there are quantum mechanical limits to information. Science, the history of science, has been the history of pushing back those boundaries. And those are the boundaries we have today, just in the physical sciences, and there's more boundaries beyond that. And so I look forward to us pushing back some of those boundaries. This is what I just said. You can't get information beyond the edge of the universe. You can't get information out of a black hole. You can dump it in, but you can't get it out. And you can't get information smaller than the quantum limit. And I'll even allow that in Tibetan for a while. Now, these are not perfect boundaries. Scientists right now wonder if there are other universes out there beyond ours, and we might learn about them if their universe expands into ours and we begin to see them appearing in our universe. Hasn't happened yet. This boundary in the black hole, I can't get information out, but there are some things that leak out. We'll find out what those are later. All right, so here's my map of the entire universe known to physics. On the bottom axis, down the bottom here, down at the bottom, it's the radius in meters of an object. And each little tick mark there, from the middle tick mark, white doesn't show up very well on white, but right down here, it says, this one right here, 10 to the 0, right here, 10 to the 0. That's a scientist's way of writing 1 meter. That's me. And, oops, whoa, that's interesting. And if I go up, hey, Stay there. If I go up from there, the arrow is pointing at man. That's me. I'm 1 meter in size. And on the left is my mass. It's the mass of something. And I'm about 100 kilograms. Okay, doesn't like me. We'll jump to this one. So my length is about 1 meter, and my mass is about 100 kilograms. And there I am standing on a mountain. That's me, about my 1 meter. And that mountain is 1,000 meters. So I made a jump of a factor of 1,000. I don't want to make the jump. And this is how it's read. So I come up 1 meter, 100 kilograms. Now the Earth is an even bigger jump. This Earth is 10 million me's lined up side to side to get from the middle to the edge. 10 million me's. And the mass is 1 with 24 zeros. It's a huge mass. It's a tremendous jump. It's this beautiful blue sphere out in space. There are other planets. Jupiter. Jupiter is 1,000 times the volume of the Earth, 11 Earths across, 300 Earth masses. Down here, if it doesn't jump on me right there, is a giant storm that Galileo saw in his telescope 400 years ago, still running. Now there's a storm. That's the biggest planet in our solar system. But as Chris told us the other day, here's the smallest dwarf planet. We have dwarf planets. It'd be nice if we discovered 2 more, then there'll be 7 of them. But this dwarf planet's named Vesta. We just went there. We have a spacecraft orbiting Vesta taking pictures. It's nice and spherical. Its gravity has pulled it into a sphere. And on the right, I show you over here its comparison. There's Vesta. Here's another dwarf planet in our solar system series. And then, of course, there's the moon for size. So there are small planets. There are big planets. And in this diagram, wait a minute. And as Chrysippus showed you, we are now finding planets beyond our solar system. When you look out at the stars within 100 light years of Earth, as of this month, there are 687 planets going around 474 stars. The smallest we've found so far is 1.6 times the mass of the Earth, and the biggest is 31 times the mass of Jupiter. So that's the range of all the planets. And so if I look on this graph, I guess when I touch it, it's going to move. If you look up here on this graph, you can see Earth and all the planets on a little straight line up there. So we're moving our way towards black holes and the edge of the universe, to the edges here. We're working our way to the edge. Well, bigger than the planets is the sun. And the sun is, that's 700,000 kilometers in radius, and 2 times 10 with 30 zeros, 1 with 30 zeros after it, kilograms. And yet the sun is just a middle-sized star. There are bigger stars, there are smaller stars. And as stars age, there's a lot of mass there. There's a lot of gravity pulling it in. And inside the sun, there's nuclear fusion, heating up the molecules, making them dance around, pushing out on the gas, keeping it from going out. If you look at the very top line of this diagram, you will see the sun, an average star, lives its life billions of years, swells up as the nuclear combustion comes towards the surface, blows off matter, and then what's left behind is the mass of the sun in the size of the Earth. There's that thing called a white dwarf out there. And then, if the star is more massive than the sun, gravity really wins out. It blows up into a red giant. It explodes in something called a supernova, and then it collapses to one of 2 things. If it's under 3 times the mass of the sun, it becomes a neutron star, and if it's more than 3 solar masses, it becomes a black hole. And black holes are where I'm going to go with this talk. And you can see that a white dwarf is the size of the Earth and the mass of the sun. The neutron star is several times the mass of the sun and the size of Delhi. So the mass of the sun fitting into the size of Delhi, that's really hard. And the black hole is more than 3 times the mass of the sun and about 30 kilometers across. Okay, so on this graph, there's a blue line up the middle. And that blue line connects everything you know from every day and a little bit beyond every day. Everything on that blue line is made of atoms. Now, Richard Feynman said, if he thought that all scientific knowledge were going to be erased from the world, and he had one sentence to convey, to start all of science again, that sentence would be, all the world is made of atoms, small in particles, continuously in motion. And he thought that would be the best start. And this blue line connects everything that's made of atoms that are touching. Stars are made of atoms that are touching. Well, they've lost some electrons, but they're mostly atoms. Planets, mountains, man, cells, the atom itself. But now you'll notice some things off that line. Up at the top on the stars to the left, you see the white dwarf with the mass of the star, but smaller. And to the left of that, there's the neutron star with the mass of a star, but smaller still. And to the left of that is a black line. You see these three lines on here, this triangle of lines. That upper left line that goes up from left to right, that's the line that tells you when any given mass turns into a black hole. If I start at a man and I go left to that line at 10 to the minus 23 meters, that's almost a billion times smaller than an atom. If you squeezed me down that small, I would become a black hole. We don't know of any black holes that size, but that line tells me where they would occur. The black holes we know are just to the left of that neutron star and up the line a bit. So a supernova can make a neutron star. Here was a supernova, 1054 AD. It went off. The Chinese astronomers recorded it. We call it the Crab Nebula supernova. This is how it looks today. It's quite a big explosion. There's a neutron star at the center. We can see that neutron star spinning and blinking. If the remnant had been more massive, it would turn into a black hole. We don't have any pictures of black holes. They're hard to photograph. One, they're black. Two, they're surrounded by bright glowing matter, which shields them. So this is an artist's drawing of a black hole. And it has this sharp boundary around it. The gravity of the black hole is so great, it bends light. When light comes around the black hole, it bends. In fact, any planet or star, when light goes by it, gets bent. The black hole just happens to be very small, very massive, and it bends light a lot. At the center of our galaxy, which we'll see shortly, there is a black hole. It's a supermassive black hole, 4 million solar masses. It's a gigantic black hole. And this is an image taken through a telescope, and the arrows here are pointing to the middle of the galaxy. You cannot see the black hole. How do we know it's there if we can't see it? The stars, the blue stars in the middle that you see, have been photographed for over a decade, and we can see them orbiting nothingness in space. There must be something there pulling on them with gravity. So we know that black hole is there. Well, we can calculate the radius of a black hole. Here's a simple calculation. There are better, newer ones that give the same answer. What happens is the gravity becomes so strong that light shot upward from the surface of the black hole cannot escape. If I shoot light up from the Earth, it escapes. If I throw a spacecraft out of the Earth at escape velocity, it escapes. Newton was quoted wrong when he said, what goes up must come down. It's really, what goes up at less than escape velocity must come down. But light cannot even escape a black hole. Now, we do know about black holes. John Wheeler said of black holes have no hair. It reminds me of monks. But what he meant by that is that information does not leak out of the black hole. We can only know its mass by dropping objects into it and watching how they fall. We can know their charge, the electric charge, and we can know if they're spinning or not, their angular momentum, because as they spin, they rotate the vacuum of space around them. But information cannot get out of that black hole. I can drop in, but then there's no trace except for my mass, my charge, and my spin left behind. So when you hear scientists talking about the inside of a black hole with things other than these three things, you have to realize that that's theory. And theory is great. It helps us, it guides us to where to do experiments. But it's not experimental science. So there's that upper line there, and you see the words realm of the black holes to the upper left. Well, now let's go to the edge of the universe. And here is the Milky Way. If you go out at night, here on a clear night, you'll see this bright band in the sky. Now that bright band we now know is stars and glowing gas and dust. And the dust gets in the way, that black band. In fact, I really loved visiting South America. The Indians in South America, the natives, actually make their constellations out of the black regions of the Milky Way. They use the solid black in the Milky Way to make their shapes and figures, whereas Western science connects the dots from star to star. Here is a picture of the Milky Way taken in infrared light. Infrared can see through the dust. This is an actual photograph of what the Milky Way looks like from the Earth. This is the image of the Milky Way that a snake would see. A pit viper, a snake that can see in the infrared. And you'll notice from this picture, we're out in the suburbs. We're in McLeod. We're not in Delhi. Delhi is the center of the Milky Way. It's that large glowing ball in the middle. We are out on the rim. We're way out there looking in at our galaxy. Well, as we look out to the galaxy and beyond, there's an important rule of physics, and that is looking out in space is looking back in time. When I see you, it took 10 nanoseconds for the light to get to me from Geshe Nima. 10 nanoseconds. He could do anything in that 10 nanoseconds. That's a 10 billionths of a second, a very short time indeed. But you can go out and look at the moon, and you see it where it was 1.5 seconds ago. You don't see the moon where it is, you see it where it was. And when you look at the sun, you see where the sun was 8.5 minutes ago. It's moved. The light takes time to get to you. This gets really exciting when you look at the stars. When you look at the nearest star other than the sun, you see it where it was and as it was 4 years ago. It could have exploded, and you wouldn't know for 4 years. At night, I took the Geshes out, and we looked at the sky, and we saw the Andromeda Nebula. That's that galaxy you're seeing on the right of that picture. And the Andromeda Nebula, the light takes 2 million years to get here. So you're seeing it way in the past. But it's the Andromeda Galaxy. And one of the great things, however, is when we look out there, and you look out, you see the blackness of space beyond. If you were to look with a radio telescope, if you look in radio waves, you can actually look back to the beginning of time. You can look back and see the light that left the Big Bang 13.7 billion years ago. So there's Andromeda, 2 million years ago, 2 million light years away. There's a cluster of 1,300 galaxies in that photo. Galaxies come in clusters. The Hubble telescope can collect very faint light. And in this photo, every dot of light is a galaxy. And that's called the Hubble Ultra Deep Field. There are 10,000 galaxies in this ultra deep field. And this image comes to us from 13 billion years ago. So galaxies had formed 13 billion years ago. And we know that this is only 700 million years after the Big Bang. So the galaxies had time to form in 700 million years. So now, on the right-hand edge here is the edge of the universe. Okay? That vertical line on the right, a constant radius, 13.7 billion light years. You can see the dot at the top there for the mass and size of the universe. And it was discovered in New Jersey. in 1965 by these two gentlemen, Arno Penzias and Bob Wilson. And that's their radio telescope that they used to hear the radio song from the Big Bang. Well, we have better telescopes today, and this is the best current image taken in radio waves. So your eyes wouldn't see this. We've coded it. It's coded information. And in this information, the average temperature you're seeing, this is a map of temperature of the Big Bang. The greens in here are 2.725 degrees Celsius above absolute zero. It's really looks cold to us. And the red is warmer by 200 thousandths of a degree, almost 20 millikelvins, 20 microkelvins, 20 millionths of a degree above that. And the blue is a little cooler. And you may think, what's this with these tiny temperatures? 20 millionths of a degree Celsius. What's that going to do? What that did, the darker areas here were cooler and moving slower. Hot things move fast, cool things move slow. They're moving slower, and gravity pulled them into the giant clusters of galaxies I just showed you pictures of. The fact that the Big Bang started out with hot and cold places created the universe we see today. And in fact, that pattern also tells us that the world we know, this atoms that I was so happy and so proud to tell you about, only makes up 4% of the universe. That image just hit scientists and told them, okay, you thought you understood the universe? 23% of the universe is something called dark matter, and we don't know what it is. We know it exerts gravity and attracts things. We can find out places where it exists, and we're on a tremendous search right now to find it. What could it be? But even worse than that, 73% of the energy of the universe is in the form of something we call dark energy, and that's gravitationally repulsive. It pushes things apart. And we don't even have the slightest idea how to look for that. So what I'm telling you is that scientists now have a really good idea of 4% of the universe, but the other 96% we're looking into. And I think people get the wrong idea about science, that we know everything, and we don't. We really don't. So the radius of the visible universe out to that edge that you saw is 13.7 billion light years. And as Chris mentioned the other day, you can actually look beyond that wall. That wall is a wall to light. You can't see beyond it with light. But if you look beyond it with particles, you can actually see the particles that come and have been created back to 1/10 of 1 billionth of a second after the Big Bang. Well, the universe expands. What's it expanding into? Nothing. It turns out that you may have this picture of the galaxies rushing apart from each other. And in fact, the modern scientific view is the galaxies are not moving through space. The galaxies have new space appearing between them and us. New space is just, new vacuum is appearing. That's the modern view of the expansion of the universe. In fact, here's a view that's likely to be disturbing. The 3 black dots at the top of this image are you. And this is a one-dimensional universe. All that exists in this universe is that curved line. That's the whole universe. It's a line. And there's one star off to the side. The thing is, if you look at the star, you see it in the past. Remember, you see stars in the past. And in the past, the universe was smaller. That's that smaller circle. So distance outward in this picture is time. So that's the old universe. And when you look to that side toward the star, you see it in the past. Now in this universe, looking in the other direction, there's no star. And so when you look in that direction, you see the light that came along that curved path from the Big Bang. You look out in that direction, you see the birth of the universe. And what is it? It's a point. And in fact, as I look in all places in the blackness of space, what I see is a point. In the 4 dimensions of space-time, we're surrounded by a point. A very strange idea indeed. And that's why it's hard to see beyond the edge, because beyond the edge is the inside of a point. Well, that hurts your brain. We are surrounded by a point. Beyond the edge of the visible universe, there is not even emptiness. Not even emptiness. I think I need some Buddhist help here. Okay, there's one more line left. That's that bottom left line. And that bottom left line, it's the limit of quantum knowledge, that we've discovered that all particles behave as waves. And in 1801, Thomas Young did the 2-slit experiment, which I'll show you about. And Richard Feynman again said, all of quantum mechanics is contained in the 2-slit experiment. Unfortunately, no one understands the 2-slit experiment. And we heard that mentioned earlier today. Here's the 2-slit experiment at the museum I work at the Exploratorium. It's not esoteric. You can do it. And what happens is, if you put a laser through a slit and have it pass through 2 slits, the light makes a pattern on the wall. Oops. And there's the pattern. The upper pattern is 1 slit. If you put light through a wall with 1 narrow slit in it, you get the upper pattern. If you open a second slit, which Thomas Young did in 1801, a different pattern appears. Blackness appears. What he discovered was light plus light equals dark. Light from 1 slit, when you add a second slit, created darkness in some places. It's an amazing idea. But beyond that, in the modern world, and in fact, even if you shoot 1 particle of light, light is a particle and a wave, if you shoot 1 particle of light at a time through the 2 slits, it passes through both slits in some ways and makes the pattern by itself. You only need 1 particle at a time to do this. And this picture shows you a photograph of the 2 slits with light going through it, 1 particle at a time. We've done the 2-slit experiment with light, photons, with electrons, with neutrons, with atoms, and with buckyballs, which are groups of 60 atoms. This means that all of those things, which you might think of as particles, are also waves. They interfere with themselves. And because they're waves, here is a picture of a wave of a neutron, for example, interfering. A neutron wave. And because they're waves, they have a wavelength. And things that are going faster have shorter wavelengths. There's the shortest wavelength possible, which is called the Compton wavelength. It's as they approach the speed of light. Here it is. And as you approach the speed of light, this Compton wavelength, you cannot ask questions about the structure of that particle that are smaller than that Compton wavelength. There's a limit to the size, the question you can ask. And, sorry about that. Oops. Okay, so there's a quantum limit. And when you hear scientists talking about things that are smaller than the quantum limit, they're pushing the edges of science. The theory can go there, and then the experiment must follow. And they're doing it. They're pushing that edge all the time. Okay, there are other limits to science. There's what is consciousness, what is mind. There's the speed of light limit, and you read recently that scientists may have seen neutrinos, a particle going faster than light, and everyone got really excited because whenever you approach one of these limits, we get really excited about pushing beyond the limit. But now other scientists will have to repeat that experiment because we don't take anyone's word for it. We must do the experiment. So if you hear scientists talking about what's inside a black hole, what's beyond the edge of the universe, that's smaller than 1 wavelength of a particle, of particles that go faster than light, realize that they're pushing the edges of experimental science. But that's a good thing. That's what scientists have always done. And scientists themselves have to remember that there are things beyond the simple world of physics that we must investigate. So is this the end of science or the beginning of the new science? I hope it's the beginning of the new science. And to show you the kinds of things that might be the beginning of, I now point you to the places on my diagram where the lines come together. At the very top, there's a red ball that says, if the thing that's there is a black hole that has the mass of the universe, you will notice that the universe we know, that black dot that I labeled universe, shows that we are not in a black hole. The universe is not a black hole. That's a nice thing to know. The dot on the left, to the left side, that says quantum black hole, that is a black hole that is a wave. And that black hole is right at the edge of science. The theoreticians are really working at that. You might have heard of it. It's called string theory. This quantum black hole, the upper line, the black hole line, is described by a wonderful physics theory. It's called general relativity. Never been shown to be wrong. The bottom left line is quantum electrodynamics. Wonderful theory. Never been shown to be wrong within the limits of measurement. But where they meet at that point, they disagree. So we have these two completely correct theories for all they've been tested, and they come together and they disagree. So we know there's great science there. And the string theorists are poking at that science, and now the experimentalists have to catch up with it. And at the bottom is a mass, a tiny mass, that has a wavelength so that only one wavelength fits in the entire universe. And that's so far beyond anything we explore. There's so much more to look at in science. So I leave you with the idea that science does have boundaries, and I urge you to go look for them.
Sir, Mr. Paul, as an astronomer, how would you connect the dots between cosmology and consciousness? Maybe you can present a different view other than Rajesh did yesterday.
Well, one thing about the cosmology, our cosmology is that we have created the human consciousness, the fact that the human consciousness can conceive of this universe, can look out at the universe and come up with some simple ideas that begin to describe it, not in its entirety, but to begin to just get a hint of it. So I think we can also look at the consciousness that creates the idea of the universe. To look out, you need the consciousness to look out. There's a great story. In the early days, astronomers looked at the planet Mars through a telescope. And on the planet Mars, they saw canals. Schiaparelli wrote a paper and he said, "I see canals on Mars." And as telescopes got better, the canals vanished. There were no canals. And it turned out the canals were created by the human eye and brain. That the dark patches on Mars, these faint dark patches through bad telescopes, the brain immediately made into lines. And so I believe it was Carl Sagan that said that the canals on Mars were the sign of conscious life. At first we thought the conscious life was on Mars, carving the canals. But in the end we know it was the conscious life on Earth creating them, the human mind seeing the canals that were not there.
토마들랑에 다 참을 뜻을 주의. 니 간주 베베 루스 상부 여반나신기 다지다네 nga 기시에기 뽑았을 때 매대 이내야 계제 시초가 치세 나와 쉬이. 당에 계제 제디 견전자부디 거와키고 있으나 시적이 캡세스예지다. 시적이 체여로 요 말에스. 지부직들도와 지부당 거야. 기대 시적이 체여버라지나 시백이 시적 같이 즉 니에 두고를 베스. 당 아주 대선다부터 드렸다. 다 디인도가라야 체리기 대시 잡다데 다게 당아주 다게 볼기 대시 참아 잡사 스타디게 돌 다 이내 딩아주 낭베기 토네 지 시제 캡제 여러웨스나 지단에 지 나랑기 고술 라고다 야 낭베 슝 디레스에 딩 시토에스 요 말에 갸체탄 띵삽탄 시토에 요 말에 이내 나랑기 고단라 준주 그 식디 사와딩이 지 챙미도 다 빼다고 간지고 요스나 룽바 강 세마 장대 버리지나 세마 레레 시파 지 교육대 버리지 육수 여러베스 라버다 디티바타인 두가라 디용네 육수 요 말레스 다 디기 탈람 가리요레스 다디 균젠 티운 두가라 니 탈람디 가리요레스 라두가라 자 한국식 콘쇼라다 다 룽바 가지 칸나 자 한국 콘나다고 가 세마 가지 요네 지 뇌견 톡 말와 디메도 자 한국식 콘레 콘쇼스 다 디벨리다 다디 된다라 가르자고 그러스나 시자 체디 레레레지 빼나 분바라지나 분발로 몽바차 레레레 가서 레레 요리다 인도갈 레레레지 체데 바라지나 체 투에 요르베스나 체 투에 요텐데리다 이네 체 깔락하고 슈시레스 딜레 야가 최든수 파샤네 랑기 심디 파 두스나 랑기 심기 디바디마 매버 수시다 대가랑기 최담지 똑사레스 다 디케제도 슈지레도 다 주고데 디인도 아주 넘버 3기비 되단스 라고 말다 다딩에 타준세도 고면 딩아랑 고다데 딘리시메도 시절의 체 요레스 이네 체백 지삼기 파체도나 땅에갈 가고 슈레스 디인자 시절기 캡제세디 조데랑 유기 셈디기 디바디 마타도나 시절기 타디가랑 예두고두스 디지기다 균지 디 남베기 공바디 덴데 멘도 다딩아랑기 섬주인다야 딩이 셰투에요 말 다디 인도갈 gemпол라게 단다 타섬시 인도갈 타섬다부데 지댕기 타섬시 송도와 다 지댕기 타섬 소인도 가르레스 라인도갈라 다 조조인도갈 보나고 블랙홀 에너지 레도와 보나고레스 다 타섬데 디송송아 디송인도갈라 다 기디 땅 아주기다 지댕기 타섬라지 르와 유어바라지 이나 체리바 찍고 지금 마임바 미규마 탐지라 하고에 체도 가지고 체리바게 디지털 배송 가능한 게 여러베스 다 집어직 딩이와 디지 데네 게 가지고 지댕기 가지고 오비 딱 까마래 내가 나시기 무sik래 덴데기 직 딱지 집을래 덴데베기 투즈다 덴데기 벤주딩이 미마 껴불라 롭좀 떼다 코유고 토라 따야다 덴데라 따나 게젠치가 요 말에 기디 땅게 여나 땅로 땅당 간체레스 다 집어 대생이인데 안 투시나.
Now, if you want to see something really impressive, Karma is now going to translate that word for word with 100% accuracy. I want you to check him on this.
No pressure.
Just to all. And so when we talk about the limits of knowledge, actually we are talking about whether our consciousness can know all the knowable things in the universe. And from the Buddhist point of view, when we talk about the knowledge and the consciousness and the knowing of knowable phenomena in the universe, in one of the mind training texts, there is an example or a story or the analogy. It says that if there's a land that is filled with thorns, and you wanted to get rid of these thorns, then there's no way that you can pick them one by one and throw them away. Instead of picking the thorns, you should better wear iron or the metal boot so that you won't harm from those thorns on the ground. Same way in Buddhism, this is the example, and same way in Buddhism it says that if you wanted to know all the phenomena, all the knowable phenomena in the universe, instead of trying to find one by one, you better look inside yourself and change your, try to refine your consciousness or the mind. And if you are able to refine your mind by removing the two obscurations we call Tibani, and if you are able to dispel these two obscurations, then you will become all the physical world knowledge will be appear to you without knowing. You don't need to go up to one by one. And in the physics, when we talk about the limits of the knowledge, the Sir Paul has given examples, 4 examples, like the null limits at the black hole and the horizon of the visible universe, and there are 4 other examples in total. And so a question related to this concept is that if the even horizon of the black hole is a limit of knowledge, then what scientists or the scientists, scientific community has done in order to make this understandable to the common people? And a second part of my question is that because of the scientific developments, we have made so many progress in different fields like economic and material developments. And I feel that if we can direct these developments or these achievements towards a betterment of a society or a more kind of a peaceful society, it would be more meaningful. And what is your stand on this issue?
Yes.
Okay, so I like the idea of the steel boots stomping down the thorns of science. And in fact, physical scientists are guilty of picking the thorns, the bits of knowledge one at a time, but then we gather them together and look at them as a whole and try to make rules and make new ideas that encompass the whole universe, like the law of conservation of energy, which we apply everywhere. And I'll use that one right now to jump to the last point, because if you understand the law of conservation of energy, then you will understand a lot about the power system that you use to power your homes, the gas and the electricity. And if you understand that law, as science teachers should bring to you the understanding of that law, then people that come to you and promise you free energy, or free energy for a price, which is what they tend to do, you'll know whether they're lying or not. So it's not just the science, it's the midpoint that he made. It's the science teaching. It's taking the big ideas that we assemble from the small ideas and spreading it to people. And I think actually in the United States that every day some newspaper in the United States mentions the word black hole. I think it is in such common usage around the United States that you will find it all the time. And so I think we really are trying to bring these ideas to everyone. And there are people who specialize, science journalists, in bringing those ideas to the world. So indeed, my answers were, yes, I agree with the points of view made, but they're not finished yet. Scientists have still things to learn, and that's why we're here, listening to these ideas from the Buddhist monastics about looking at the world as a whole.
That's a great answer. And now it's time to move on. David Presti is. Bryce, are you introducing?